Hello everyone, my name is Rania. Today we will be talk about preparation of wine. Let's begin by looking at how volumetric analysis plays an important role in wine production. This method is all about using volume-based techniques like titration to measure key substances in wine, such as acid, sugars, and alcohol. These components are crucial because they affect how the wine ferments, how it tastes, and its overall quality. For example, we can measure glucose and ethanol levels to monitor the progress of fermentation. We can also track the wine's chemical chains to predict how it will taste later. And importantly, we measure tartaric and malic acids to make sure the wine stays microbially stable and tastes just right. This process basically follows a chain: glucose to ethanol and finally wine. What's even more interesting is that all this data can be used in mathematical models to help predict how fermentation will go and even how the wine will smell and taste in the end.
Hi everyone, I'm Umu. Let's talk about volumetric analysis, a key technique used in wine lab to measure important chemical components that affect wine quality and stability. So what is it? Basically, it is a method where we react a solution of unknown concentration with one that we do know, called the titrant, until the reaction is complete. That point is called the end point, and we usually detect it with a color change or a pH meter. This method is super useful in winemaking, especially for three main things. First, titratable acidity. This tells us how much acid is in the wine. It's measured by titrating with sodium hydroxide, and it gives winemakers an idea of the wine's sourness or freshness. Second, we have volatile acidity. Volatile acidity measures acid that evaporates easily, mainly acetic acid, the stuff that makes wine smell like vinegar if there are too much of it. We usually distill the wine first, then titrate to find the volatile acidity. And the third one, we have sulfur dioxide. Sulfur dioxide helps preserve the wine and prevents spoilage. We measure it using a redox titration with iodine or a method called aeration oxidation. Why is volumetric analysis so widely used? It is accurate, affordable, and perfect for routine checks, which is why winemakers rely on it to ensure every batch meets their standard. That's volumetric analysis in a nutshell, a simple but powerful tool that helps keep wine tasting great.
Volumetric analysis in wine is a simple and useful method to find out the amount of different substances present in wine. It helps measure total acidity, volatile acidity, sulfur dioxide, and alcohol content. Before doing the test, the wine sample is usually filtered to remove any solids and may be diluted with water if needed. The process of titration involves measuring the wine using a pipette, adding an indicator, or using a pH meter, and slowly adding a titrant from a burette until there is a color change or a change in pH. This change shows that the reaction is complete and the amount of titrant used is recorded. Different chemicals are used for different tests. For example, sodium hydroxide with phenolphthalein for acidity and iodine with starch for sulfur dioxide. To find the result, we use a simple formula. Sometimes the titrant also needs to be standardized to ensure the accuracy. The equipment used includes a burette, pipette, volumetric flask, pH meter, and analytical balance. During the process, it is important to avoid oxidation, use fast reagents, calibrate instruments properly, and prevent the evaporation of alcohol or other volatile substances.
We boil while we steam the wine. And the idea is we trap as the steam pushes through the wine. Once it gets through the wine, boil off the valve. And then it's starting. There we go. There we go. Oh, baby, look at that. Yeah, this is why you drink a lot on the job, because you're waiting for these things to happen. No, wait, there's more! There you go. It's got a yes button. Probably. So you got bubbly things going. So you got a bubble here, you got a bubble there, lots of colors, and a beer in my hand.
What is it doing?
What it's doing is it's aspirating. This is acidified wine. So we have wine in here, and we have phosphoric acid to acidify it. And I'm aspirating air bubbles through it, which draws the sulfur dioxide gas out of the wine, runs it through the hydrogen peroxide. World's fastest chemical reaction. Hydrogen peroxide, sulfur dioxide, yield to sulfuric acid. Bang. So it changes from green, gray to purple. So now we know we have sulfur dioxide in here, and after 10 minutes, all of it should be aspirated out of here. And then I titrate it out with sodium hydroxide solution to determine how many parts per million of sulfur dioxide we have. This is in a billion order, and the patent was issued back in 18 something or other. I paid $750 plus for it. It won't work at 5300 elevation. Water should boil around 100 degrees centigrade.
Now let's look at a titration example to better understand how the values are recorded and interpreted. We have a table here showing the burette reading for 1 row titration and for accurate titration. The 3 key columns we're focusing on are the final burette reading, the initial burette reading, and the titrate, which is the volume of solution delivered from the burette. In the row titration, the final reading was 17.15 ml and the initial was 0.65 ml, so the titrate is 16.15 ml. This helps give us an idea of what volume range to expect in the accurate titration. For the accurate titration in the first trial, the titrate is 15.95 ml, in the second is 16.45 ml, the third is 16.55 ml, and fourth is 16.15 ml. From this value, we can see that the titrate are consistent, especially between titration 2, 3 and 4. This showed good precision, and we would take the average of the closest concordant titrate, typically within 0.10 ml of each other, to calculate the final result. This example highlights the importance of repeating titration until consistent results are obtained, ensuring accuracy in experiment. In this part, I'm going to show you the calculation on how to measure acidity in wine.
Now, let's talk about how we can measure the acidity in wine using titration, specifically to determine the amount of tartaric acid present. We begin with the balanced chemical equation at the top. 1 mole of tartaric acid react with 2 mole of sodium hydroxide and produce 1 mole of sodium tartrate with 2 mole of water. So, firstly, we calculate the average titrate volume using 3 trials provided, which are 16.5 plus 16.45 plus 16.55 plus 16.5 divided by 4, and we will get the 16.15 ml. So here are the volume of sodium hydroxide. Then we calculate the number of mole of sodium hydroxide using the formula N equal to Cp. C is concentration and B refer to the volume. Okay, before we calculate the number of mole, we need to change the volume ml to liter by divide with 1000. So we will get 0.0165 liter. And then we substitute the value. C is 0.097 mole per liter. Multiply with the volume is 0.0165 liter, and we will get the number of mole for sodium hydroxide is 1.61 multiplied by 10 to the power of negative 3 mole. Next, we find the mole of tartaric acid. Since the ratio from the equation is 1:2, we divide the sodium hydroxide mole by 2. So, mole for tartaric acid is equal to 1/2 number of mole for sodium hydroxide 1/2. We already know the mole for sodium hydroxide is 1.61 multiplied with 10 to the power of negative 3 mole, and we get the answer for number of mole of tartaric acid is 8.00 multiplied with 10 to the power of negative 4 mole. From this, we calculate the concentration of tartaric acid in mole per liter using the formula C equal to N over V, where the volume of wine is 0.02. So, we substitute in this formula. Number of mole for tartaric acid is 8.00 multiplied by 10 to the power of negative 4 divide with the volume of wine is 0.02 liter, and we will get the value is 0.040 mole per liter. Okay, in this step, we need to convert mole per liter to gram per liter. So firstly, calculate molar mass of tartaric acid, and we get the value is 150 gram per mole. So we multiply 150 gram per mole with 0.015 mole per liter. So equal to 0.040 mole per liter multiplied with 150 gram per mole, and we get the answer 6.0 gram per liter. Finally, to express the result as a percentage by volume, we use the formula mass solute divide with the volume of solvent multiplied with 100. So we substitute the value into the formula. Mass solute is equal to 6.0 gram per liter that we get from the previous calculation. Divide with the volume of solvent is 1000 ml multiplied with 100%, and we'll get the answer is 0.16% of tartaric acid in the wine. This is how we can quantify acidity in wine through titration.
Okay, here are the titration curve. This graph shows a titration curve for a weak acid and a strong base. A weak acid is tartaric acid and a strong base is sodium hydroxide. At the beginning, the solution is acidic, so the pH is low. As we slowly add the strong base, the pH rises gradually because the acid is being neutralized. When we reach the equivalent point, shown in the middle of the steep curve, all the acid has been neutralized by the base. Because it's a weak acid and a strong base, the pH at the equivalent point is above 7, usually around pH 8 or 9. At this point, adding more base causes the solution to become strongly basic, and the curve level of this titration curve helps us understand the strength of acid and base, and the correct indicator to use is phenolphthalein, which change color in the basic range.
In conclusion, volumetric analysis is important to ensure wine quality, safety, and regulatory compliance. Volumetric analysis is widely used in the wine industry to quantitatively determine the key components such as sulfur dioxide and titrable acidity, which directly affect the wine's stability, taste, and shelf life. The titrable acidity of wine are able to provide insights into the organic acid content that influence the flavor of the wine and fermentation progress. Through volumetric analysis, winemaker can accurately measure free and total sulfur dioxide, which is essential for controlling microbial growth and oxidation, thereby preserving wine quality and extending shelf life. The technique is valued for its reliability, accuracy, and relatively simple execution, making it suitable for both small winery labs and large-scale production environments.